Yeah, hello, good morning, good afternoon. Welcome to our webinar today. The webinar today has the title Joining of Brittle Aluminum Castings and Mixed Material Designs with Self-Pierce Riveting. It's actually a pleasure and honor for us today to give you an update on our latest innovations in self-pierce riveting, particularly focusing on castings. I have the pleasure to do that today with my colleague Jan Schneider from Product Management. He will lead you through the vast majority of the slides later on. So I have an easy job this time as I just lead you through the introduction slides. My name is Matthias Wissling. I made my PhD in 2007 on joining technologies. As Vice President for Research and Development, I do the utmost possible together with the team to make sure that we have technically outperforming solutions for your challenges. So next slide, please. So we are from, I think we can skip that slide and go to the Stanley Black & Decker slide. So we are from Stanley Black & Decker. That is a huge global company with about 17 billion revenue per year and about 56,000 employees. Stanley Black & Decker is organized basically on two main pillars. One is the tool and outdoor business, and the other one is the industrial business. Jan and myself, we are from the Stanley Black & Decker industrial business, which is mainly Stanley Engineered Fastening. We at Stanley Engineered Fastening, we have about 80 production and distribution centers all over the globe. And you can find our products in 90+% of all automotive vehicles and lightweight trucks on the road today. Next slide, please. So we at Stanley Engineered Fastening consider ourselves as a development partner for our customers. We have not one solution, but multiple solutions in order to make sure that we can always supply you with the best solution for your challenge. On this slide, you see a selection of some of the technologies we can offer you. So we have stud welding, of course. Here we are, as with the other joining technologies, we have the equipment to automatically weld the studs in your production line as well as the studs. And we have here a no-hole solution. So this is 100% water and gas tight. Then on top right, we have our self-pierce riveting technology. Also here we have the equipment as well as the rivets, the fasteners, and we also do the joint designs to support your body-in-white structures. Number 3 is our blind fastening technology product line. Also here we have a great variety of different kinds of blind fasteners, including pop nuts, a great variety of different hand tools, as well as fully automated solutions, and a fully automated solution will come to the market this year. A relatively new part is our plasma assistant joining technology. So here we are using plasma for the joining operations. Also here that is a one-side accessibility, and that could act, for instance, as an alternative to FDS. Next slide, please. So of course, electrification is a main strategic pillar for us. We offer all the joint and fastening solutions for the battery, as well as on top of that, we are developing innovative solutions on the most challenging technical problems we see about the battery, like safety, fast charging, range, etc. So therefore, we develop solutions for thermal management as well as for pressure management, such as vent plugs. Next slide, please. Yeah, sustainability in Stanley Black & Decker is a huge topic, of course. What does it mean for the different product lines? We would like to illustrate that here with self-pierce riveting. So on the equipment side, we can offer you solutions with less power consumptions and less air consumptions. And we are working on an airless equipment solution, which will come to the market soon. On the equipment side, I mentioned a few topics, but also on the rivet side, we have a couple of interesting solutions here for you. For instance, we developed new rivet generations which save about 64% of CO2 emissions for you. And it's not only a benefit in terms of sustainability, but since we developed here a very lean solution, we have also a very cost-effective solution here. So a solution that can compete successfully with spot welding on total cost of ownership side. Okay, next slide, please. Here is already the time we have the pleasure to hand over to Jan, who will lead you through the casting related slides. Thank you.
Thank you very much, Matthias. What a great introduction to the topic and to my person. So my name is Jan Schneider. I'm the product manager for our joining technologies, meaning everything that joins sheets together in one way or another. So SPR, or also single-sided technologies like the new one, plasma joining. And today we want to talk about SPR and castings. And the question is SPR still the best way to join your castings? And before we go into that, I want to remind you or give you the information that we have a chat box. And in this chat box, you can enter your questions. At the end of the webinar, we might have 10 to 15 minutes, depending on how many questions are entered, to answer the questions as best as possible. And of course, we try to answer all the questions. So whenever you have a question to what I say or what you see on the screen, just write the question of interest into the chat box, and we will go there at the end of the webinar in the Q&A session. So before we start to talk about SPR and castings and why do we need to do a webinar and what are the challenges, etc., I'm sure some of you, or maybe most of you, already have experience in that or are aware of the challenges. So where I want to start is at the beginning. So I want to start with the history of SPR and castings. Here you can already see a lot of pictures. So on the left side, for example, the picture on the left side, that's a typical aluminum casted shock tower. These shock towers in different varieties from different manufacturers you can find since many, many years. Actually, the first one was close to in the 2000s in an Audi car. And you can find them in many, many cars like upper middle class, upper class on the road right now. You can also see a wheel arc or wheel arcs and other structures on the side and under body that are done since long time, actually, with aluminum castings. So these castings are like from middle small to middle size. Middle meaning, not when I talk about mega, I mean the really big ones that you're about to see. So when I talk about only these castings, I'd call it just the middle size casting. And most of these castings are joined with SPR, especially because you connect them to other materials like mixed materials. Then we have all the solutions to join these materials, but these materials are also heat treated. So why do we have to do a webinar if we are doing this since 20 years successfully and the cars are not breaking down on the road? That's what brings me to the next slide. What is the change? What changes right now and what is the trend in the market? What changes first is everything gets bigger. So you can see from different manufacturers or OEMs, they present their strategy and their view of the role of aluminum castings in the automotive industry. So you can see that the castings are clearly getting bigger, from a complete underbody or a complete back and front part of the car, and everything gets bigger. But does it get better? First of all, I want to talk about why is this trend even existing and what are the benefits for the OEMs to use this kind of big castings. First of all, on the left side, you can see the trend that we are observing right now, meaning on the bottom side, you have the conventional manufacturing, meaning a body in white consists out of hundreds of parts, and you have joining technologies, you have gluing, you have assembly technologies, you have welding, you have everything, and a lot of parts that are combined at the end, the body in white, the BIW, right? BIW, yes. But now the trend is more into the directions of make the casts bigger. First of all, what the first benefit is, you get a reduction of parts. Of course, if you can combine 100 parts into just one part and have the same functionality, the same complexity, whatever, why not? Second is, you can save costs and CO2 because you will not heat treat these big castings. You need to figure out a way how to use them without heat treatment, which means in F-temper state. So then, because then you can really optimize the costs and the CO2 savings as well. And then, of course, you have the reduction of assembly processes, the reduction of joining processes, which is not really good for me as I'm doing joining equipment and fasteners, but this is the benefit for the OEM. And of course, you can have really good cycle times, really fast production cycle times, because a lot of processes are now sourced out to the manufacturer of the casting, and you don't need them anymore inside of your plant. There are more benefits to why you would use mega castings, and some of them are, for example, you can further increase the lightweighting potential, or you can make more complex structures, or you can integrate functional elements directly into the cast. So from this page on, for everyone, it should be clear why they want to use, or you want to use, the market wants to use mega castings for the body in white production. But are there any challenges with that? So now I want to talk about the challenges first and then step to the solutions. Challenges, yes, because the casting is for sure the fastest way from the material, raw material, to the final functional part. But is it the best way? And what is the downside, or let's say the challenge, not the downside, the challenge of that? First of all, you can have imperfections, or you will have imperfections in the cast, meaning you can have pores, holes, cracks. You can see pictures here on that slide from a hot crack, for example, shrink porosity, die soldering, when the material is gluing against the tool, the press, and then you rip out some of the material. You can have these imperfections. You can have pores up to 3 millimeter or even bigger. So we have to admit that there is no perfect mega casting, and maybe never will be a perfect mega casting. It's more about when the manufacturer and the user connects, and they need to define how many imperfections are still okay, how big are they, where can they be, and just to define these rules to make sure that the part is still functional and can still be used, but you will never get a perfect one. So we have to deal with these imperfections. Other questions that you have to ask yourself as well, or the OEMs are asking these questions, is what about the crash performance of castings, and what about repair if something breaks? It gets really difficult to repair something if a car is at the peak of the trend, just consisting out of one cast, one big mega cast, then it might be hard to do something on the repair side. But are there more challenges? And yes, there are. So for example, this is now more infecting us as a joining systems supplier, the mechanical properties for these castings. So on the left, you can see a graph, which is elongation at break to tensile strength. And the blue one is a 5000 aluminum alloy that you most of you know. And the yellow ones are drawing are the current casting alloys that we see on the market and that are used for these mega castings. So you have ALSI 7, ALSI 10, and a lot of mixtures in between. But what they all have in common, especially when they are not heat treated, they are brittle. They have a reduced ductility based on elongation at break. So I use the indicator elongation at break I use elongation at break as an indicator to say something about the ductility of the part or the material. We know that there are more indicators that say something about the ductility, the complete ductility of a part or a material, but I use elongation at break in this case, and going further, we'll keep on using elongation at break as that defining ductility value. In here, you can see a 10% line, and this is some kind of a magic line, let's say, because a lot of people talk about when you talk about SPR, is it above 10% elongation or is it below 10% elongation? So this is sometimes, or you can hear it often, the rule like, oh, if you are below, you cannot use SPR. Is this really the case? We will see. But just to sum up this slide, so we have a reduced ductility, we have an increased porosity, and we have the situation of brittle fractures and not ductile cracks. Ductile, that means a ductile crack is that the material is not stretching and you can see it stretching and at some point it gets thinner like a rubber and then breaks. It's more like a spontaneous crack, because if you try to bend and deform this material, it's more like glass. If you want to bend and deform glass without making it hot, for example, it just breaks and shatters. So it's the same with these materials. But there are even more challenges, and this is why we have to have this webinar. So at the end, there are also challenges in the part design, and the reason for that is that the material itself, the cast itself, is inhomogeneous, meaning if you have one part, it's the same alloy, but depending on where you do the joint or where you do the material testing, is it close to the entry of the aluminum? Is it close to the end of the aluminum? What is the flow direction? Do you test vertical to the flow direction? If you do your tensile tests, do you test in the same direction as the flow direction, etc., etc. So there we see different features and different mechanical properties on the same part. So in the past, you can see a nice button there on the page. In the past, we would just select for your material combination, we would select the perfect rivet and the perfect die. We would do settings, we would do cross sections, we would check the button, and then we say, okay, that's the rivet and die for this combination, works perfect, your interlock is good, all of that, right? But now the situation changed, because only 2 centimeters to the side on the same part, we see this. So we see, oh, now there are cracks on the surface. They are not really deep, but you can see some cracks on the surface of the cast with the same rivet, the same parameters, and the same die. So you do another one close to the second one, 2 centimeters on the side, and you see again something else. You see, oh, there's a hole now, and there is a deep crack. Deep crack, when I say deep crack, I talk about cracks that go really deep. If you do the cross section, they go really deep up to the rivet itself. So basically the material is completely broken at one side. And you do the fourth one, and then you can see, oh, there is the hole again, which was not there in the first and the second one, but on the third one. So you have many different outcomes on the same part, because this material is inhomogeneous, right? And one addition that you can also see or find is the closer you get to the flange edges, you can have flange cracks. So, but this is also not always the case, but the closer you get to the flange edges, the higher the risk you get a crack. So when you aim for a perfect button without cracks, it seems to be that there is more stress into the surroundings of the material, so that the chance is higher to get a flange crack. So with this results, you actually might to think about redesigning the flange size, and some of the OEMs are already doing that because they are aware of this issue, right? So this is the last issue that I can show you here on inhomogeneous material. So how do you work and how do you deal with these imperfections and these challenges when you want to join them at a consistent rate, to reach the right CPK values and be okay and don't have high ppms? So the first thing that you need to do is you need to do a lot of testing and you need to do a lot of failing, meaning we have done over 1,000 tests on these materials, different ones, and we saw many different failure modes. So you can have flange cracks, all the problems that you have seen in the slide before. You can have holes, you can have surface cracks, you can have a complete crack where the button falls off the sheet. You can have insufficient interlock, you can have all of these issues. So first thing is you spend the time in the lab, you get the material, which is sometimes not that easy to get the material if you're not a manufacturer of these materials. So you get the material, get your specimen and do the tests and fail. And then you work out of these failures, you try to understand what's happening and how can we improve our rivet and die designs to support these materials. But testing takes a lot of time and it's a lot of work. So in addition, we need to do something else, which is on the next page, please, which is a simulation. So we also, on top of all the testing, we also use simulations to simulate the material flow inside of the die so that we can see how the material behaves and how the rivet and the die behaves and how the material flows and where are the highest pressures and where is the highest stress on the material. And this helps us also to determine new geometries or new rivet and die geometries for these castings. On the next slide, you can see now what came out of this testing. So these rivet and die solutions, and I will go through each one of them, these are our solutions for castings. So you can see on the top, there are three pictures. These are the dies. And on the bottom, you can see 5 pictures. These are rivets. Some of the rivets are completely new, like came out this year or still coming out, will come out this year. Same as one die on the top, in the top row. And other rivets were already existing or other dies were already existing. So let's start with the first one. First one is just the flat die. I'm talking about the die, not about the rivet in the first picture on the top left. So it's a flat die that you can use for more ductile castings, meaning if they have a T7, right, or a T6 heat treatment, then you can use them. These flat dies are perfectly working. Then the second picture, it's a casting die that we developed, and you can get that with flow barrier feature or without flow barrier feature. In this picture, there is the flow barrier feature existing, and you can use this die for lesser ductile castings. And then the newest development, the fancy geometry that you can see on the right, on the top, that's the special casting die, and that's a mixture of the casting die and some improvements to really support the material flow and to be sure that we have a really low risk or no risk to get any cracks with F-temper. That's what I talk about the most when I talk about these castings, F-temper castings, mega castings. Then we have new rivets. The first one is the CDH. Actually, it's not that new. We already had that since a few years. but we have it improved in size. So now the CDH can be used for soft aluminums and soft castings that you can join together up to a thickness of 12 millimeters a stack. So 12 millimeter stack of material you can join with this rivet. Then on the next, on the right, the HSA rivet stands for high strength aluminum. You can use this also to a thickness up to 12 millimeters, but it's a little bit similar to the CDH, but it can withstand and pierce through stronger aluminums and stronger casts. You know, the castings are sometimes 150 megapascal, but they can also be 300 megapascal. So maybe you need to determine what kind of rivet for these applications, okay? And then when the joining partner gets more challenging, meaning a harder steel, high strength steel, we have the HSS rivet, and brand new, the S rivet for joining HSS steels or even higher, up to 1000 megapascal in 1.6 millimeter thickness, with these rivets into F-temper mega castings. ALSI 10, ALSI 7, all of those work. And if you go even harder, like even harder steel, you need to go to the U-rivet, and we also have some success there, but it's depending on the material thickness of the steel. On the next picture, on the next slide, let's say, you can see some examples. So in these examples, we used a DP600 to a 3 millimeter aluminum casting, and we used different castings. You can see the alloy information, ALSI 7, ALSI 10, and the first picture is F-temper, meaning no heat treatment, elongation between 5 and 11%. The next one is T5 temper, and interestingly, T5 is worse than F because the elongation is even lower. So for those low ductile castings, brittle castings, we use the special casting die. And then if you have the more ductile castings like the T6 and T7 ones, we can use the flat dies, and all of these results that we show are without cracks. So these are all okay joints that can be used, that can be run in the car, on the road, in your production. Nothing will fail, okay? But now I have shown you rivet and die solutions. We are a system supplier, and we also supply the process, meaning for us, you can only withstand and overcome these challenges when you look at everything that you offer that's around SPR and the process and the rivets and everything, right? So in the last years, we have followed a rule that our process is a distance-driven, a travel-driven process, travel control, I call it. So we drive to a position. It's a position control, rivet head height, right? We drive to that position and we monitor the force for sure, but it's not a force-driven process. We still have the rivet length measurement, the sheet thickness measurement, and all of that. But what we did in the last years was we have not seen any difference, or not noticeable difference, if you want to run the system slower or faster. So we compared different setting speeds with our system. So we ran it at 300 millimeters per second, we ran it at 200 millimeters per second, or 100 millimeters per second. And we compared the results, and there was no reason really to go lower in speed for 99.99% of the cases. Okay, so we always said our speed is not adjustable. You go with full speed, best cycle time, and that's how you set the joint. But now we reconsidered that, and we said, you know what? The market is so developing so fast, and the materials are developing so fast, and maybe in 2 months there is a new patent for a new alloy, and it has different behaviors. So we said, okay, we saw that it can be helpful on some of these material combinations in combination with mega castings, brittle mega castings. It can help to run on lower speed. So now with our new software update, which is available for the ones that have our new generation, you are able to program the speed down to 50 millimeters per second and all the way in between. And maybe that at some point will also help your joint. After all, when we talk about all of these solutions, so new rivets, new dies, and also a change or a more adjustable process when it comes to the setting speed, we can say that we were able to join all of these alloys for these brittle mega castings that we have seen so far in the market and that are used. So for us, the 10% elongation rumor or rule or whatever you want to call it, because it's not written anywhere, like it's not in a physics textbook that this is the number, but maybe you encounter this. So this is not applicable for us because we have also joined 5% elongation brittle castings. So far, we can say that yes, SPR is still the best solution for your cast. But what happens when it gets even more challenging? So we have talked about the casting, so the bottom material and the deformation of it and the cracks and all the challenges that come with the casting. But now let's talk a little bit about the joining partner. What happens if the joining partner is an ultra high strength steel, 1500 megapascal, 2 millimeters, or 1800 megapascal or 2000 megapascal? And we see this trend going up that basically the use of these steels increases, but of course you have to have a solution to join them, because a 2000 megapascal with mechanical joining, that's quite difficult, right? So why do you want to use them? Maybe because you want to increase the lightweighting potential with these steels, and maybe you want to have a better crash performance, because in combination with the castings that are weaker on the crash performance, maybe that's a perfect solution. So what happens when you do the brittle casting together with the ultra high strength steel? Here you can see what I'm talking about. So on the right side, again, it's the elongation at break to ultimate tensile strength graph. The yellow one, the yellow circle that you can see, that's the F-temper castings. They are around there. And the blue one on the right side, that's the ultra high strength steel up to 2000 megapascal. So in this case, what you need to think about is you want to join these most critical components, materials together, one on the left side and one on the right side. It doesn't get any more challenging than that. So what you would do, you would check, okay, I need a rivet that can pierce through the ultra high strength steel. So I choose a rivet. But I also need a rivet that supports the deformation of the brittle aluminum cast and the correct die for it. And the same rivet will not work for that. So what can we do about that? And at next page, please. Yeah. At that point, I want again to emphasize you to answer. No, not. Yeah, you can answer your own questions. That's also good for me because it's already late. Just submit your questions if you have questions. For sure, at the end we will try to answer all of them. But let's go on. So now we need to talk about SPR innovations. Again, the question was, what do you do in this situation where you want to join the 2000 megapascal to the brittle F-temper mega casting? We thought about many different ways, but we came up with one really nice solution. Oh, and this is our plasma. So I'm sure most of you have already seen this because we have shown that at the Automotive Circle joining in Bad Nauheim this year and the last year already with our plasma joining, with a single-sided joining technology. So most of you are maybe aware of this? If not, we use a plasma with argon gas to heat up the top layer. And we did use this plasma. It's a non-transferred arc, so we are just shooting a flame on top of the material. And we first use that in our stud welding systems to clean aluminum sheets because they have dry lubricant and all of this. So we clean that to have a better aluminum welding results on the stud welding side. And there we don't make anything soft. We just clean the surface. Then we thought about, okay, now we use that for plasma joining to pierce through 2000 megapascal with our plasma pin. Why not connect this to an SPR system as well? Because standard, or let's say traditional SPR, also has its limitations. So how that works is pretty simple. You will see that on the next video. This is a slow motion video, and you can see that we are shooting the plasma on top of the, in this case, Uzi bore with 2000 megapascal. Oh no, this case is 1500 megapascal, I'm sorry. And then we just directly after that set the rivet, join these two combinations. So it's Uzi bore 1500 megapascal into an aluminum. And you can see that the process overlaps a little bit and that it's quite fast. Okay, this is slow motion, but it's really quite fast. So we use the plasma, which is, by the way, around 2 centimeters away from the top metal sheet. We use the plasma to make the Uzi bore soft. We don't want it liquid. We just want it like orange gluing to make it soft. Okay, and then we pierce through the Uzi bore with a rivet. And of course, why I want to talk about this in our castings webinar is we, of course, also supply some heat to the bottom layer because the heat is traveling through the stack. So let's see some results of that. These results have also been shown on the joining event in Bad Nauheim. But again, I want to talk about the first one that I highlighted red here. So this combination is a 2000 megapascal Uzi bore with 1.55 millimeters into an F-temper aluminum cast. And we used, as you can see, a rivet in H4, so not hardness 6, just hardness 4, with a quite basic rivet geometry and a flat die. And we were able to join this combination without cracks or without any other problems with the rivet, because if you would try to join this material with this kind of rivet, you would just press the rivet flat and that's it. You would not be able to pierce through this material with any kind of rivet. Okay, so we see that, remember, flat, I told you before on traditional SPR, you can use a flat die on the more ductile castings. Now we can use this on the really low ductile castings as well, because we use some heat. We heat up the stack. In the next slide, you can see some other effects and benefits of that. So you can see here four force curves, and the force curves look different than what you would expect when you just set these kind of ultra high strength steels and compare the curves with one another. So first of all, the force is much lower. So the end force is much lower. Usually what happens is that the force of the setting peaks when the rivet head touches the top material and presses into the top material. This is where you get the 80 kilonewtons or above, right? But if the top material is still a little bit soft, you don't get that peak. So you are at the highest at this one. It's a little bit far away, but I think it's 64 kilonewton was the highest one that we got on these trials. And remember, that's a 2000 megapascal 1.55 millimeter on the top sheet. And in addition to that, so lower forces, end forces, you also have a much lower punch stroke, meaning usually when you do that with traditional SPR, you need to punch through the ultra high strength steel, and whenever you can have the chance, or maybe you have already seen or heard how that works, you can hear it in the whole line, right? So it can sometimes be really loud if you punch through these materials with an SPR. So if you have multiple machines, it can be quite noisy in your manufacturing area. Of course, when you make it soft, orange gluing, you don't have that punch stroke. You can see it's much lower. A much lower punch stroke also means less stress in the equipment, because every punch is vibration and stress for the equipment, and also less stress in the material that you're joining. So that's another benefit. Now we talked about the top layer, how to get through the top layer, but I already said that we are talking about mega castings here. So now let's switch back to the mega castings part. We are joining these combinations easily with a flat die, because we transport heat from the top to the bottom, and heat always helps elongation, so it makes the material more ductile. You can see here on the left side that the bottom of the steel was 560 degrees. The middle of the aluminum part, which was sorry, I can't read it, what it was. The middle of the aluminum part is 140, yes, 140, and the part on the bottom 120. Thank you. Maybe I need glasses, I don't know, or we need a bigger screen. So yes, we can transport the heat down, and you can see that already with the difference between like room temperature 20 degrees to 140 degrees. On the right side, you can see a graph that's an example for 5,000 alloys. You increase the elongation at break values, which means you increase the ductility, which means you have an easier life in joining these brittle materials, and you don't get cracks with that. Okay, but again, we are shooting from the top, and heat is traveling through the bottom. Okay, at this point, actually, I would normally end the webinar, but I have one more thing, or two more things that I want to show you. And the first thing is really a world premiere, because I have seen the results just a few days ago, and this is the next thing that we want to do on the SPR side. And it's, who would have thought, I mean, maybe all of you had the idea already, we are doing SPR from the bottom now. So all the slides that you have seen before was SPR from the top, but the good thing on SPR is we have a two-side access, which means we can also use the plasma from the bottom, right? So using the plasma from the bottom enables two things. First of all, it makes SPR a solution for a new joining direction, a more extreme joining direction for SPR. It's a soft in hard. So you can see a cross section on the right, where you can see that we joined aluminum into Usibor 1500 megapascal, and it worked fine. And the second benefit is that you, of course, when you have the plasma on the die side, you can even more control your bottom layer. So we can use it on the top side or the bottom side, depending on where is the more critical material. Use it from the top and have some heat transferred to the bottom, or if your top is not a problem, but you have really low ductile, maybe recycled casting that looks like a puzzle and you can break it with your hands, maybe you have a really bad material, then maybe you can try with plasma from the bottom, and then you get really nice results. And of course, the plasma is freely programmable in time and energy and power, meaning you need more power for the Uzi bore to pierce through it. But if you only need a few hundred degrees in the aluminum, you don't need that much power, right? So you can freely program it depending on what is the material combination that you have, and you're good to go. So this is the next step. As an overview now, on the left side, you can see plasma from top, and plasma from top, again, to pierce through the Uzi bore into the aluminum cast, transfer the heat to the bottom side, and this will be ready to be shipped to the first trials at customers, meaning you, in Q1 next year. So we will be able to ship the first systems for line trials. We have done a lot of trials in our lab already, but we will be able to ship systems to you next year. So if you're interested in testing this, and if you have the need to test this or use it, then just contact us and we will be able to maybe arrange something with you to get a system and do tests together with you so that you can see by yourself how great this technology is. And then on the right side, we have the plasma from the die side that I spoke a lot yet now in the last slide. And plasma from the die side is currently in prototype testing in our advanced engineering. So it takes a little bit longer to get a system that we could ship somewhere. We are still learning and testing it. So this will take a little bit longer, but will be existing at some point. Now, the cherry on the cake before we end the webinar and go to the Q&A session, upgrade your existing TRC, meaning this plasma process is a complete optional process that you can put on and upgrade your current existing TRC equipment. 100% flexible means you only need to upgrade the guns, the tools that might have this kind of joints, these critical joints, like Uzi bore on top, Uzi bore on the bottom, or brittle materials that you want to join with plasma. And 100% optional means even when you upgraded one tool to the plasma with a plasma function, you can still use it without the plasma, and the plasma will not come in your way. It will just stay at the rest position. You can do your normal aluminum to aluminum with your rivets. And once there is an ultra high strength steel that you could not do with that rivet, you just add the plasma feature, you turn on the plasma, and you do the setting with the same rivet, if the length and everything, if that matches. So that's the best benefit from our side on the equipment side as well for plasma. This is the end. Thank you very much from my side and also from Matthias' side for your time today. I would like to welcome now Mr. Obermann and Mr. Wissling again on the stage so that we can talk about the questions that hopefully have been submitted, and hopefully we can answer them.
Yeah, I hope everybody can hear me.
Yes.
And the very first question I will ask is the one which makes me most nervous. It was the first question which came up very early during this webinar. And the customer asked the question as follows: to join low pressure casting, that's the keyword for me. In the past, they used flow drill screws because SPR couldn't be used for that. I immediately answered, yes, we will discuss this during the upcoming webinar. Is this true? So basic question, tell me what low pressure casting is, and maybe later we need to ask the person who asked the question, is everything answered or not?
Yeah. Wolfgang, let me try to answer this question. So low pressure aluminum casting. So we have, let's say, a molten material such as aluminum, for instance, which we press into a cavity. And for low pressure casting, I think the maximum pressure, gas pressure you are using is 0.8 bar. So that has some implication on the casting. So usually there is a minimum thickness with these castings. So it's about 3 millimeter. And The mechanical properties, however, usually from what we have seen, are relatively good. So the vast majority of the casting joint evaluations, we are doing this with high pressure die cast materials. Low pressure castings, I think your answer was correct. Since the elongation, the ductility, and also the fracture behavior is okay, as long as we use the new rivets and dies Jan just presented. On one of the slides, there was also an information about the length of these rivets, because if you have thicker castings due to the production process, you need also longer rivets, and we just increased our portfolio also to cover thicker applications where you need longer rivets. And would like to conclude with the offer that please don't hesitate to contact us. We would like to do some tests for you in order to show you that also with real samples. Good question.
Okay, so the customer who asked this question, hopefully this answer satisfies what you expected. If not, get in touch with us, describe what you have not heard today and what you need to get answered. And as always, Matthias, he's fantastic to talk, and I'm sure he will talk about this question as well. EcoSmart, we talked about the EcoSmart rivet briefly, but I think there are some customers who don't even know the story about EcoSmart. Tell the story, but in a reasonable time.
Yeah, I do my best. It's late anyhow here. Yeah, absolutely. So basically that started this entire evaluation and development because of two things. Customers were more and are more and more interested in sustainability topics. So we get more and more questions. How high is your CO2 emission footprint? Number one. Number second is that, of course, we see for pure aluminum joinings, we see also competitive joining technologies such as aluminum spot welding. And customers, they like the mechanical strength of self-pierce riveting joints, and they want to keep it. But at the same time, they don't want to invest, let's say, more than what would be the case with spot welding, for instance, where there is no fastener. So the target was develop something with low CO2 emission footprint at the same time with a significant cost reduction. And that is the story behind this EcoSmart rivet, so that we can significantly reduce the costs for the fastener, and we can significantly 64% reduce the CO2 emission footprint of these fasteners. Was that short enough?
It was great. Great.
Thank you.
Now I think I have a question. Jan, you can answer. Okay. And it's again interesting listening to the customer's question. They see things I now have seen as well, so I can ask you on the video. You've shown the video for plasma joining, and there was a ring in the video shown. It looks like the plasma goes into a cup, and the question is, doesn't this limit the accessibility? So what is this ring all about?
Okay, yeah, I understand. So it was on the slow motion video of where you saw the plasma. Okay, yeah, this is not part basically of the equipment, and this is just on the functional mock-up that we use in our lab. This is just a device to hold the specimens. So we enter the sheets inside of this device just to make them static, and then we can join. Right? So this is not part of the the system. This is just for the lab, so that they don't lose their material. Yeah.
Okay. Can we get a video without this?
Maybe then you have hands.
No, that's too dangerous from a safety perspective. Okay, yeah, I think there's time for one more. Do you have made tests with glue in between the top and the bottom layer?
Yes, we have already made.
That's a short question. Answer: yes.
Yeah, yes. So on one slide, actually, there was an example of Betamax, I think, was in there, or what's the name of it? So we have made tests with adhesive between the layers, because of course in mixed materials, in 90% of the cases, maybe we use adhesive, and this is why we tested it. It works, for sure it works. It has one thing that you need to think about is the adhesive can isolate the heat transfer a little bit more or support the heat transfer because you have something in between. So depending on how much your top layer is an issue or your bottom layer is an issue, you need to decide what to go, like plasma from top, plasma from the bottom, or maybe traditional SPR where you don't have an issue with that anyway. Anyhow, so yes, we have tested that. We have results that we can show. If you want more details on that, just let us know and we make sure that we send you some results of that.
Okay. Last question. We've shown the plasma video. You talked a little bit. It's a slow motion. What's the cycle time? What's the complete cycle time compared to a setting process without plasma?
Yes. So the plasma time for this was an USI-BOR 1500, I believe. The plasma burning time is between 1.7 and 1.9 seconds, and the setting time is 1 second because this processes overlap. So in total, this process for this video that you have seen was below 3 seconds, was 2.8, 2.9 seconds, and that was the complete process time. But the plasma burning time, of course, you can freely program. If you don't need 800 degrees or something in the USI-BOR, if you just need 400 or 300 in the aluminum, you can go shorter. Yes.
Okay, I think by now we almost passed the hour. So thanks for the questions. Whenever additional questions are coming up later during the day, please forward them to us and we will try to answer them as quick as possible. So thanks for your time. And
great. Thank you. Bye-bye.